A fully loaded 747 carries over 57,000 gallons of fuel. Nearly all of it sits inside the wings, and most people assume that's simply about available space. It isn't. That fuel counteracts the bending forces generated by lift itself, reducing wing root stress by up to 20%. The real reason aircraft keep fuel in the wings goes far deeper than storage. And it starts with a problem measured in centimeters. Aircraft designers face a balancing act measured with precision. Every large jet must keep its center of gravity, often called CG, within a narrow band, sometimes just a few centimeters wide. This balance is not a matter of convenience. It is a strict requirement for safe and efficient flight. If the CG shifts even slightly outside this window, the aircraft can become unstable or difficult to control. The challenge is that fuel itself represents tens of tons of mass, and as it burns off, the CG can move forward or aft. On a Boeing 747, for example, a full load of fuel weighs over 380,000 pounds, enough to shift the CG by several feet if not managed carefully. To prevent this, engineers place most of the fuel in the wings, where its weight is distributed close to the aircraft's neutral balance point. This arrangement helps keep the CG steady throughout the flight, even as thousands of gallons are consumed. The margin for error is slim. Modern jets are designed to keep the CG within a band as narrow as 5 to 10 centimeters. That tight control is only possible because of careful fuel placement, making the wings not just storage spaces, but critical tools for stability and control. Lift acts relentlessly on an aircraft's wings, pushing them upward with forces that can reach hundreds of thousands of pounds in flight. This upward force creates a bending moment at the wing root, the point where the wing meets the fuselage, putting the structure under immense stress. Engineers solve this problem by using the weight of fuel inside the wings as a distributed counterweight. Instead of concentrating all the downward force at the fuselage, the fuel's mass spreads along the span of the wing, directly under the regions generating lift. The effect is measurable. Flight test data from aircraft like the Boeing 737 show that when the wings are fully loaded with fuel, the peak bending stress at the wing root drops from about 250 megapascals to 200 megapascals during a 2.5 G maneuver. That's a 20% reduction, enough to allow lighter, more efficiency spars without sacrificing safety. On wide-body jets, the relief can reach 25% at takeoff. This isn't just theory. Strain gauges and finite element analyses confirm these numbers, validating the practice across generations of aircraft. By turning fuel into a structural ally, designers achieve a dual payoff: lighter wings and lower stress, both essential for safe, efficient flight. During World War II, the Boeing B-29 Superfortress set a new standard for fuel storage by making the wing itself the tank. Instead of relying on separate rubber bladders or external pods, Boeing engineers built sealed compartments directly into the wing structure. This so-called wet wing design allowed the B-29 to carry an enormous 9,363 U.S. gallons of fuel, spread across multiple inboard and outboard tanks, plus additional capacity in the bomb bay when needed. Self-sealing liners protected these tanks, swelling shut when pierced, to prevent catastrophic leaks from enemy fire. With this configuration, the B-29 could fly over 3,600 miles without refueling, enough to reach distant targets across the Pacific and return. The engineering team, led by figures like Eddie Allen, faced daunting challenges: keeping the tanks leak-proof under battle damage, venting them safely at high altitude, and ensuring the fuel load didn't overstress the wings. The result was a bomber that not only outranged its predecessors, but proved the value of integrating fuel into the wing's very bones. This breakthrough made the B-29 the first mass-produced aircraft to use a fully integral wet wing, validating the concept under the pressures of real combat and setting the stage for every large aircraft that followed. When Boeing engineers set out to create the 747, they faced a scale never seen before in commercial aviation. The aircraft's wings alone hold 57,285 gallons of fuel, enough to fill more than 100 average backyard swimming pools. The wings provide this massive capacity. This vast capacity is not just about range. The 747 can cross 7,260 nautical miles with a full load. The true advantage comes from how this fuel is integrated into the wing structure. By distributing nearly 400 tons of fuel along the span of the wings, designers achieve a double benefit. The fuel acts as a counterweight to the upward force of lift, and it allows the main wing spar, the backbone of the wing, to be built lighter than would otherwise be possible. The 747's wing box design spreads the mass where it most effectively relieves bending stress, keeping the structure strong yet efficient. Managing this volume requires careful planning. Every drop affects the aircraft's balance and performance. The sheer scale of the 747's wing tanks shows how fuel storage has become an essential part of the aircraft's structural and operational design. On the Airbus A380, fuel management has become a fully automated, high-speed operation. 11 separate tanks are monitored and controlled by the Fuel Control and Monitoring Computer, or FCMC, which constantly calculates how fuel should be shifted to keep the aircraft's center of gravity within a precise target band, usually between 15 and 35% of the mean aerodynamic chord. This is not a static process. As the A380 cruises, burns fuel, and encounters turbulence, the FCMC uses real-time sensor data to command 12 pumps that can transfer fuel at rates approaching 50,000 kilograms per hour. These transfers are not just about balance, they also dampen slosh, minimizing rapid shifts in mass that could affect roll or pitch. The system is so precision that it can limit roll variation caused by fuel imbalance to less than 0.1 G, a level undetectable to passengers but essential for flight control and structural longevity. Automated sequencing means the outermost tanks are emptied first, drawing mass inward and keeping the center of gravity in the optimal zone for efficiency and stability. This invisible choreography of pumps, valves, and sensors is the product of years of engineering by Airbus's automation teams, who designed the A380's fuel system to act as a dynamic ballast, adapting instantly to the changing demands of flight. Supersonic flight brought demands that no subsonic airliner had ever faced, and Concorde answered with a fuel system unlike anything before or since. At Mach 2, the center of aerodynamic pressure shifts dramatically aft, threatening to push the nose down and overwhelm the flight controls. Instead of relying on massive tail surfaces or brute force trim, Concorde's engineers turned to a subtler solution, using fuel itself as a movable ballast. By pumping up to 20 tons of fuel from forward tanks to the rear trim tank, the flight engineer could shift the center of gravity rearward by as much as 6 feet, enough to keep the aircraft balanced through the entire supersonic cruise. This translated to a 2 to 3% movement along the mean aerodynamic chord, precisely matching the aerodynamic shift as the aircraft accelerated through the sound barrier. The process was mostly automatic, coordinated by the flight engineer's panel, but manual override allowed quick corrections if needed. The pumps and transfer lines had to work flawlessly at 60,000 feet, where outside temperatures dropped below minus 50 degrees Celsius and pressure differences could cause vapor lock. Every transfer was a carefully timed dance, keeping Concorde stable and efficient at twice the speed of sound. This system didn't just save fuel, it made Mach 2 flight possible, turning the very meaty mass of the aircraft into an active part of its control system. On July 17, 1996, TWA Flight 800 exploded off the coast of Long Island, the result of a spark igniting fuel vapors in the center wing tank. Investigators from the NTSB traced the cause to a combination of residual fuel, heat from air conditioning units beneath the tank, and an electrical arc that set off a catastrophic chain reaction. The oxygen level in the tank's vapor space was high enough to support combustion, a vulnerability present in many large jets of the era. In response, regulators mandated a new standard. Fuel tanks must be inerted with nitrogen-enriched air, reducing oxygen below 12% and pressurizing the ullage to 2 to 5 pounds per square inch. This requirement, known as SFAR 88, now applies to all new commercial aircraft, making nitrogen inerting a non-negotiable layer of protection against fuel vapor explosions. Jet fuel stored in the wings does more than power engines. It shields the aircraft from the extremes of temperature encountered at altitude. At cruising heights, outside air can plunge below -50 degrees Celsius, threatening to freeze fuel and damage sensitive components. Jet A fuel, with a freeze point near -47 degrees, must stay above this threshold. Maintenance engineers monitor these temperatures closely, knowing that even a small drop can cause waxing or gelling. To prevent this, fuel is often circulated through heat exchangers, absorbing waste heat from hydraulic systems and engine oil. On modern jets, this process can remove up to 150 kilowatts of excess heat, keeping the fuel temperature within a safe range, typically between 0 and 45 degrees Celsius. Additives can shift the freeze point closer to -30 degrees, providing a margin for safety. This thermal management is not just about avoiding cold. It also prevents hot spots that could damage pumps or trigger alarms. By using the wings as both reservoir and radiator, engineers ensure durability and reliability, even on the longest, coldest flights. Wings endure decades of expansion and contraction as temperatures swing from -40 to +70 degrees Celsius. Aluminum alloys in the tanks expand by about 0.0009 per degree, and jet fuel itself can change volume by nearly 0.8% over a typical flight. By designing tanks to flex and move with these cycles, materials specialists extend the wing's fatigue life by as much as 5%. This careful engineering keeps the structure reliable, flight after flight. Every modern jet, from the Boeing 747 to the Airbus A380, relies on wing fuel for structural integrity, efficiency, and safety. With wing root stress reduced by up to 20%, this design remains essential as aircraft grow larger and flights stretch farther. Engineering keeps evolving, but the principle endures. Thanks for watching.